So, let's talk about one of the most fundamental ideas in all of electronics, the parallel circuit. But hey, we're not just going to stick to the textbook here. We're going to see what actually happens when the math we do on paper meets a real live circuit. Let's find out if theory and reality actually line up. All right, here's our game plan. First up, we're going to get our heads around what a parallel circuit even is, this fork in the road idea. Then we'll get into the nitty-gritty, the actual rules that make these things tick. After that, we'll look at the tools you need, and then we'll put the theory to the test. Finally, we'll see how our calculations stack up against the real world, and, most importantly, why any of this matters in the first place. Okay, let's dive right in with that fork in the road. What does it actually mean when we say a circuit is wired in parallel? Yeah, this picture pretty much nails it. Think of the total electric current, which we call I, as a river. It's just flowing along, doing its thing, until bam, it hits a junction. At that point, the river has to split. Some of that flow, IA, goes down one path, and the rest of it, IB, goes down the other. And you'll see each of those new paths has its own little obstacle, a resistor, which is going to affect just how much of that current can squeeze through. And this right here is the million-dollar question, isn't it? A diagram is one thing, but how do we prove this is what's really happening? How can we possibly know beforehand how that current is going to divide itself up? And more to the point, how can we be absolutely certain that our math is actually right? Well, that is exactly what we're here to figure out. All right, so before we start plugging things in and making sparks fly, we've got to know the rules of the game. Turns out there are 4 key rules that are supposed to govern every single parallel circuit. So let's walk through them.
Okay, rule number 1, and this one might actually surprise you a little. The voltage, and you can just think of that as the electrical pressure that's pushing the current along, is exactly the same across every single branch. So that push that the electricity is getting is identical on path A and path B. It doesn't matter what the resistance is. Same push, everywhere.
So if the push is the same everywhere, why isn't the flow the same? Well, that's where rule number 2 comes in. Even though the voltage is constant, the current, the actual amount of electricity flowing, is different for each path, and it all comes down to resistance. It's pretty intuitive, right? If path A has less resistance, it's an easier road to travel, so naturally more current is going to flow through it. And this is where things get really, satisfyingly simple. The total amount of current that leaves the power source is just the sum of the currents in each branch. That's it. Nothing gets lost, nothing is created. You just add the flow from path A and the flow from path B, and you get the exact total flow you started with. And guess what? The final rule, it's the exact same idea. Just like with the current, the total power the whole circuit is using up is simply what you get when you add up the power being used in each separate branch. It all adds up. It just works. All right, enough with the theory, right? Let's get our hands dirty. If we're going to actually build this thing and test it for ourselves, what do we need? Let's have a look at the toolkit.
So here's our essential kit. We've got our 2 resistors, the things that'll give the current a reason to split. We have a breadboard, which is basically our canvas. It lets us plug everything in without any soldering. For power, we've got a simple 9-volt supply, some cables to connect it all, and then the star of the show, the multimeter. This is the tool that's going to tell us what's actually going on inside our circuit.
And now for the fun part. We are officially leaving the clean, predictable world of diagrams and equations and stepping into the real world of physical components. It's time to see if our perfect theory can survive contact with reality.
This flowchart is basically our roadmap. You could even call it our battle plan. It's the scientific method, really, just boiled down to a simple 4-step process that'll take us from a calculation on a piece of paper to a real confirmed result.
Let's just break that down real quick. Step 1, we predict. We crunch the numbers using those rules we just covered and figure out what we think we're going to see. Step 2, we plan. We look at our nice, neat diagram and figure out how to lay it out on the breadboard. Step 3, we build. Time to actually connect the wires and place the components. And finally, step 4, we measure. This is the moment of truth, where we hook up the multimeter and see what the circuit is actually doing. And that brings us right here. We've done the math, we've built the circuit, we've taken our measurements. Now, it's time to compare.
This is the question at the heart of all applied science, of all engineering. Does the clean, perfect math on the page actually hold up in the messy, unpredictable real world? Let's find out.
This table is where it all comes together. That calculated column, that's for all the values we figured out with our formulas, our predictions. And the actual column? That's where we'd put the real numbers we got straight from our multimeter. We'd look at the predicted current for branch A and compare it to the measured current, the predicted voltage versus the measured voltage. This is where we see if we were right.
Okay, so we've gone through all of this, the theory, the build, the measurements, but so what? Why does any of this actually matter? What's the big takeaway here?
See, what we've done is so much more than just check our homework. We've proven that the rules of electricity aren't just some abstract ideas in a book. They're reliable, predictable, physical laws that describe how our world actually works. It's the reason the lights in your house are wired in parallel, so if one bulb burns out, the others stay lit, because they're all on their own separate path. We've taken a theory and proved it's true.
And that really leaves us with one last big idea to chew on. This whole process, theorize, build, measure, compare, it's not just for electronics. It is the engine of discovery. If you can use this simple method to prove the laws of a tiny circuit, just imagine, what other ideas, what other theories could you put to the test?